So in this video, we're gonna practice some reactions of alkenes. And this video is just for practice, so you could pause the video and just kind of predict products on your own as the answers will be given here. So let's look at this molecule. All right. So what if we were to take this molecule and we add osmium tetroxide in the first step, and then the second step we add NMO. All right, what would be the major product? Well, again, it's helpful to know these reagents are dihydroxylation. So we're formally adding two water molecules across a double bond. And so in terms of stereochemistry, we could have the methyl going away. Now remember, this gives you the syn addition. So you're going to have one OH group here, and then the other OH group is simply on the same side. Now, because they're a chiral center, this is a chiral center, and also this, we're also going to get the enantiomer. All right, let's look at another one. What if we had this molecule, and we add MCPBA, which is metachloroperoxybenzoic acid, in the presence of some acid workup in the second step. What would be the product? Well, again, this is a dihydroxylation reaction, so we're formally adding, we're making a diol here. Now this gives us the anti-addition of the hydroxyl groups, so therefore we're going to have one OH going away and one OH coming out at us in replace of the carbon-carbon double bond. Now, because they're chiral centers, we're also going to get the enantiomer. All right, what about this one? And I know a lot of people struggle with stereochemistry, so I'm going to try my best to do a lot with stereochemistry here. So what if we had this reaction, this molecule, and we add H2 in palladium? Well, again, this is catalytic hydration. And remember, the hydrogens are syn to each other, so we get them on the same side. So we could kind of show these methyl going away, and then the hydrogens on the same side kind of coming out at us. All right, and this will be the product. Notice that the hydrogens are syn addition over the carbon-carbon double bond. Now again, you could also get the hydrogens going away, both hydrogens going away, and the methyl, both methyls coming out of you, coming out at you. It doesn't matter. Just make sure your hydrogens are syn to each other. Now, what if you add this molecule? And you added ozone in the first step, and then DMS in the second step. What would be the products? Well, again, you cleave the double bond, and then you replace on either side of the cleavage with oxygen. So you're gonna get two products. You're gonna get one that looks like this, with an O right there on this side, and then you're gonna get another one that looks like this. There's our ketone. There's your aldehyde. All right, so that is just literally cleaving a double bond. How about this one? And we added hydroboration. What would be the major product? What would be a major product? Well, again, notice that this is less substituted. This is more substituted. Now, hydroboration, remember, there's syn addition in terms of stereochemistry, right? So you're going to get your alcohol on the least substituted part of the carbon-carbon double bond, and this will be your product. Now, in terms of stereochemistry, now if they ask you to show stereochemistry, this will be your product. All right, so what if we had the CH3 kind of going away? But now, I guess because there's syn, we're gonna have this hydrogen kind of coming out at us. So therefore, our OH has to be coming out of us also, and then the other hydrogen that's here is just going away. Right. So this will be the kind of product in terms of stereochemistry. Right. So this will be the product in terms of stereochemistry. And certainly you could have the OH and the hydrogen both going away from you, and these kind of coming out at you. It doesn't matter which one. Just remember anti-addition and syn in terms of their addition. So anti-Markovnikov rule, I'm sorry about that. Anti-Markovnikov rule and syn addition in terms of how they come together. Now, what if you add this molecule and you add bromine gas in the presence of water? Water in the second step. What would be the major product? Well, again, remember this follows the Markovnikov rule, with them being anti-addition. So our OH will be on the more substituted part of the carbon-carbon double bond, and our halogen will be on the least substituted. So maybe we could give this CH3A dash, or OH. We'll get a wedge. And then because they're anti-addition, that means my bromine or my halogen has to be going away from you. Now, because they're chiral centers, I'm also going to get the enantiomer. Right. How about this one? And again, as we're going through it, you could pause the video and kind of predict the products on your own for practice. All right, so what if we add this molecule and we added mercury acetate in the presence of sodium borohydride? Well, again, all we're formally doing is adding water across a carbon-carbon double bond, with now our OH being on the more substituted part of the carbon-carbon double bond. So there's two hydrogens out here, right? There's one hydrogen here. So this is more substituted. So therefore, alcohol has to be on this carbon. So we should get something that looks exactly like this. Now, how about this? What if we add this molecule? And we added iodide gas, I2. All right, well, again, in terms of stereochemistry, anti-addition. So across the carbon-carbon double bond, maybe we could show the methyl going away. One of these iodide is coming out at me. Now remember, anti-addition, so therefore the other iodide has to be going away across the carbon-carbon double bond. All right, or vice versa. You could get it the other way, where you could change the chiral centers, where you have this iodide coming out at you and this iodide going away. Either or, it doesn't matter. Just remember, we add two halogen across a carbon-carbon double bond, and with them being anti-addition of each other. Now, what if we had this reaction here, this molecule, and we added sulfuric acid in the presence of some heat, right? What will happen? Well, again, this is acid promoted, classic E1 mechanism. We're going to get an alcohol Markovnikov rule, right? So we're going to get a product like this. Again, notice that this has no hydrogen, so this is more substituted than this that has only one hydrogen. All right, so again, Markovnikov product, OH being on a more substituted part of the alkene. What about this? What if we had this and we added HCl? Well, again, this is just the addition of HX across a carbon-carbon double bond, and so this follows the Markovnikov rule, where your chlorine will be on the more substituted part of the alkene. All right, how about this one? What if we added this? We added this molecule and we added MCPBA, which is just a peroxy acid again, in the presence of an acid workup. What will be the major product? Well, again, we're forming a diol here. In terms of the stereochemistry, there's going to be anti-addition, right? So maybe we could show one of the OH going away. If they're anti-addition, the other one has to be coming out. and then we have the methyl kind of going away. All right, now because they're chiral centers, we'll also get the enantiomer. All right, how about this one? We've had this molecule and we added osmium tetroxide in the presence of NMO or DMS, some sort of solvent. All right, what will be the major product? Well, again, we're forming diols here, but we're dealing with syn addition now. So maybe we could show the methyl going away. Syn addition. The OH there coming out at you, but because there's syn, the other OH also has to be coming out at you. And because again we have chiral centers, you are going to mention that we have those enantiomers also. All right. What about this one? Simply enough, and we added HI. Right, well, again, this is just addition of HX across a carbon-carbon double bond. We have one hydrogen here. We have two hydrogens here. So this is more substituted. So that tells me that my iodide will eventually be on this carbon. And we'll get something that looks like this. Now, what if we add this molecule and we add HPO4? Well, again, sulfuric acid, we're forming an alcohol. So we get, this should be a carbon-carbon double bond. We get the OH being on the more substitute part of the carbon-carbon double bond. All right, so we get a product that looks like this, and our hydrogen, there's our one hydrogen we added. Now notice while I was doing these reactions, I drew up my hydrogens. It is very helpful. Don't force yourself to just like try to get the answers without kind of making sure you're getting stuff right. So if you could draw the hydrogens out, I recommend that. Now there's something important that I want to mention with the oxidative cleavage of alkenes. All right, when you use ozone in the presence of DMS, notice that when you cleave this carbon-carbon double bond, the molecule never changes. So you actually don't get two products. You get one product with two different functional groups. So again, we cleave that and we get something to look like this, where this is a CH3, and then we kind of draw the same molecule, that O right there, and we have a hydrogen here. So notice we get a ketone, we get an aldehyde and a ketone, and we could convert this into a line structure if we want, but that's not the point. Notice that these molecules this is one product, we get just two different functional groups. So anytime you have a cyclohexane ring, anytime you have a ring, you will get one product with two different functional groups. But suppose you have something like this, right? And you added the same reagent. Notice how you get two different products. So now you get something that looks like this with an O right here, and you also get another one that looks like this. So notice you get two products here. And the reason I'm telling you this is because when we start talking about retrosynthesis, right? So what if I were about to give you these two products and say, what is the starting material? Then, you could just simply put these together and you get your starting material. But in terms of, what if they give you this as a line structure and ask you what was the starting material? You don't want to kind of split things up. It should give you a cue. It should give you a clue that you're dealing with a ring, with the double bond being in the ring. Yeah, so I guess that's my point. When the double bond is in the ring, you form one product, and possibly it depends on, maybe depends on the molecule, but you form two functional groups, all likely. Whenever the double bond is not in the ring, you'll get two separate products. So when it comes on to providing starting materials, makes you visualize and just help you along the way a bit much more.